So just to recall what we have discussed in the last class, we have solved a given problem as a dual using the duality theorem. What we have done is, so for given problem, we convert it into the dual and then we apply simplex. And then we have seen the duality theorems which are applicable, and the duality theorems can be summarized in this form. Also, we have seen the complementary slackness. For a given, if x star is the primal optimal solution, these are slack, dual slack. This is dual optimal, dual basic variables. Optimal. So this is dual basic variables. And this one was primal slack variable. Since these are actually vectors, x is actually of this form x1, x2, or xn. Y is also similar type, but the number of variables is ym. U is variables u1, u2, um, m, yeah, and v is u1, u2, pn. So if we multiply them, then we will get this product is 0. Since all of them are non-negative, all these are actually non-negative. This is also non-negative. Okay, non-negative. So that is why we can say that by component wise, they will become 0. Xi, Vi, and Yj, Vj. Oh, this is a very powerful theorem for a given problem. If the solution of the primal is given, then we can find the solution of the dual without applying the simplex algorithm. Okay. So today we are going to look into some more aspects of dual. That is the mathematical explanation of dual. And then what is the economic interpretation we can make from the dual prices. And then we see a new method, it's called dual simplex method. So that we are trying to explain today. So in order to explain the mathematical explanation of the dual prices, so what we do is actually, let us try to add some, this was the resource 1, and this was our resource 2. Okay, so if you remember what are the meaning of resources, so let me just give you that one example from the Let me just yeah. So here, if you remember those the first problem that we have discussed in the formulation stage. So there we have seen that resources are actually, that was yeah, budget was resource, then space was resource. So if you increase the budget by some amount, delta amount, and if you increase the budget, or if you increase the budget for delta amount, anyone, you can increase the both, and you want to change uh, the this small amount of change, what will be the profit change, whether we can improve our profit or we can reduce our cost, what will be the effect of this change. So there is for resource 1, and x1 is the number of quantity that we are going to produce for a particular product 1, and x2 is the product 2. So if you reduce, I mean if you increase, there is, now let us add that as a, yeah, 5 plus delta. Then what will happen for this problem? Assume that, let us assume these two are actually still remains the basic variables at the optimum. Then what we will have? The question is how much it will be changing. If we add delta amount for this resource, how much change we can see here in the profit or the cost functions. That can be explained in this way. So if we just add, for example, the first constraint, we are adding delta x2 5 plus delta. Then we have 3x1 plus 2x2. This becomes 12. Now, in order to solve it, let us multiply this equation by 2 and this equation by 1. So this will become 2x1 into 2x2, and this will become 10. So this is becoming 2 delta. Let us subtract. Okay, so this will get cancelled. Then minus x1 equals to minus 12, 10 minus 12. Plus 2 delta minus 12. So that is x1 becoming again 2 delta minus 2. So this is x1 equals to 2 minus 2 delta. Now if you substitute this value in this first equation or the second equation, then you will get x1 plus x2. There was 5 plus delta. So x1 we have already found now. Okay. So this is 2 minus 2 delta plus x2 will be 5 plus delta. So 2 delta will come in the right side and 5 minus 2 will be 3. So x2 will become 3 plus, So 2 delta plus 1 delta, so 3 delta. So now we have found the values of x1 and x2. This is the updated values. Okay. Then we'll substitute these values here, x1 and x2. So this will become 8 times 2 minus 2 delta plus 6 times 3 plus 3 delta. If you just calculate it, this will become 16 plus, sorry, not plus, negative 16 delta plus 18 plus 18 delta. So this will become 34 minus, not minus, this is plus 2 delta. So now we can see that our z becoming this value. Now for this problem, we have seen that optimal value is 2, 3 and okay, x1 equals to 2, for x2 equals to 3, we have optimal value as 34. So if we increase 1 unit delta unit, of resource 1, if we increase delta unit of resource 1, delta unit of resource 1, then z value, objective value actually, objective function value increases 2 delta unit. Okay. Now if you actually in place of delta, if you increase 1 unit, so this will cause 2 unit increment. Okay. So this is, let us understand the meaning of this increment and the change. So at the optimum level, the objective function increases 2 delta times units if we increase the first resource by a small amount of delta unit. Again, we have seen the dual solution. The value of the first resource of the first dual variable is actually y1 star equals to 2. So here we have seen 2. Okay, and y2 star is also 2. So here also, if you try to understand, if you try to solve it in this way, if you put here delta, then you will again see that there is a 2 delta increment. So the meaning of this sentence is the value of the dual variable at the optimum. So when it is optimum, when we have reached the optimum level, at the optimum level, the rate of change of the objective function for a small change in the resource is actually nothing but the value of the dual variable. So here we are seeing 2 delta. So this 2 is actually the rate of change. So if we put here delta, so this dual variable, because this is first constraint will correspond to the first dual variable, second constraint correspond to the second dual variable. Okay. So mathematically it says that if we increase, this is the rate of change, the dual variable are actually, remember, at the optimum level. Okay. So this is the actual meaning of the word dual. Now how can we interpret, what is the interpretation of this dual variables in the economic sense? So let us understand. Okay. So just now we have seen the 2 unit of increase in the objective function if we change the first constraint for 1 unit of change in the first constraint. The objective function increases 2 unit. So if we have to buy a resource, if we have to buy a resource, we will be willing to pay maximum of 2 rupees. In place of, it is not, I don't think this is only 2 rupees. Okay. 2 rupees is nowadays very small amount. When this is just a mathematical number, for example, if it is 2000 rupees, or it can be 20,000, or maybe 2 lakh, okay, depending on the situation. So this 2 rupee is just for our mathematical purpose, for explaining the situation. Okay. Otherwise, so if we pay more, actually, then what will happen? We will be making a loss, or it will not be profitable, because at the optimum level, the dual variables are actually this much. Remember, we have to minimize for dual variable. We have to minimize 8y1 plus 6x2. No. That was 5y1 and 12y2. Here it is 5y1 and so if now that optimum level, these variables are 2, here also it is 2 for this problem. For some other problem, it can be 3 or 4 or some other numbers. But for this time, let us consider this problem. So if you actually paying, if you spending 3 or something, for example 5, so it will increase your cost. So we wanted to minimize the cost, but if you pay more than 2 rupee, then you will be making a loss. So in managerial perspective, so what we say is actually these are the marginal values. So this is the margin you can go. For example, for this slide, this is the margin. Okay. If I go beyond this, so I am violating some rules and regulations. So this is the meaning of marginal values. So dual variables are actually, the values of the dual variable are actually known as marginal values. How much we can go. So up to here, I can go up to here. But still, it is possible to write, but this is not so clear. This is not so visible. So if I write here in the white background, so it will be visible, but it is not so visible in here. So corresponding to the resource at the optimum, the marginal value of this. Okay. Now, if you just try to more, if we want to understand more detail, so let us recall the carpenter's problem, where he or she wants to make, where he makes the tables and chairs for selling purpose. So this is a table and chair manufacturing company. If you are working in this company, then this carpenter will try to buy the raw material from the supplier. Okay. And then if, for suppose, if the resource 1, if the resource 1 is less than 2 rupee, so if it is less than 2 rupees, then the carpenter will happily buy. Will happily buy this raw material, and he can make, or he or she can make profit. Then the actual problem it allows. So for suppose this is less than this resource 1.5 or 1.7, 1.2 or something else, the resource price, then the carpenter can make more profit, because this marginal value is actually 2. So it can go at the optimum level, the marginal value, it can go up to 2. Okay. On the other hand, if the seller, if the supplier, raw material supplier, sells this product more than 2, if the resource is actually now value is more than 2, then the carpenter will not buy, because it will make carpenter's loss, and the objective cannot be fulfilled. So the supplier will also be trying to increase his profit, and the carpenter will also try to make his profit and try to increase his profit. So if this resource 1 is sold at 2 rupee, only then both of them are actually happy, they are actually balanced. Otherwise one of them will make a loss otherwise. So both will be agree to purchase the resource with the competitive environment. So let us not make only one happy, let us both be happy. Okay. Now this event you can relate to your real life. Whenever you go to purchase in any local shop, for example, you try to buy any t-shirt, or if you go for any jeans, so then like we bargain. But if you go to this shopping mall or other things, so there is a fixed price or something else, where bargaining is possible, where you can make your, where you can save some money. There you can apply this duality theory. Okay. Now similar comparison can be drawn in the interview process. As a candidate, since all of you are final year students, so you must be appearing in the interviews. So they will try to, while bargaining your salary or job work, so you have to bargain something. So they will have some need, and you will have some need. Okay. But if you want to be selected, so you need to perform. That means delta amount of improvement should have 2 delta amount or 3 delta amount of impressions. So if you can improve your resources, what are the resources for your, your skills, your maybe some programming skills, education skills, some leading skills, programming. If you can add some properties or some skills like programming or leading or some other things like So these are actually treated as, so this is delta 1, this is delta 2. So you are adding value to this, to your CV for getting the selected in the job interview. So if you can improve your, so the marginal value will help you to make this happen. So this duality theory can be related to your real life examples also. Okay. So apart from that, let us discuss further. So this is actually related to let us apply this is iteration 1, iteration 2, this is iteration 3. So at the optimum level, we have seen the complementary slackness property holds, and they will satisfy these relations because all of them are greater or equals to 0. So they will satisfy these relations. Now whether they will satisfy these relations and will it provide the optimum solution, let us understand in a so for example, if we apply complementary slackness properties in this complementary slackness conditions, okay, in the second iteration, then what will happen? So take iteration 2 and apply the complementary slackness conditions. So here we can see that basic variables are x3 and x1. x1 and x3 are basic variables. So definitely we can say that the corresponding, so let me just write down, not x3. I should have written here, this is u1 and u2. So this is u1, okay, and yeah, let us write u1 and u2. So u1, u2. So x1 is 4 here, and u1 is 1. x1 is 4 and u1 is 1. So since they are basic, so the corresponding non-basic variables are v1 and y1, because if you remember, so x1 star and then x2 star we have seen at the optimum. So u1 star at the optimum level, star meaning the optimum level, and u2 star. Okay, and we have seen that corresponding to this we will have v1 star, v2 star. Then for u1 we will have corresponding to that dual basic variables u1 star and y2 star. So now what we are telling? We are telling that x1 is 4, x1 star is 4 and u1 star is 1. So if we take this situation, then these two are 0. So the corresponding non-basic will be, so since these two are actually basic variables, so the corresponding non-basic variables are this one. So this will be 0 and this y1 will also be 0. So now the basic variables are v2 and y2. So the basic variables are v2 and y2. So if you just substitute, sorry, here v2, v1 0 and y1 0. Yeah, so if you just substitute 0 here, So this is 0. Okay, and V1 is 0. So from first equation, what we have 3y2. So if you just put 0 here and 0 here also, so y2 equals to 8 by 3, and we can find that they are V2. Substitute this value in this equation, and V2 becomes negative. So this indicates that V2 becomes invisible. So the dual is invisible now. Okay, so we cannot conclude that we have reached the optimality. Okay, so complementary slackness conditions can be applied to any of the iterations, but remember, the dual will be feasible only when the table is optimal. Okay, so this is the important observation from the complementary slackness property. Now, this is another beneficial property of the simplex method. It can read both of the primal and the dual solution. So, whenever you solve this problem, then the simplex algorithm is actually solving the dual variables also. For example, if you write it u1 and u2, so u1 and u2, then you will note that, so this is actually corresponding to v1, v1, v2, this is y1 and y2. Only difference is we have a negative sign. Okay, so this is, so dual variables can be found in the Cj minus Zj row, and the primal values are actually found here. Okay, this is the primal solutions, and these are actually the dual solutions for this particular problem. For a different problem, if you think about, if we solve it in a different way, so primal solutions, and this would be called as, these are actually dual optimal. Only thing, remove the negative sign. Because we know that, because we know y1 and y2 greater equals to 0. So if you take the negative, that will not satisfy. So that is why you have to remove the negative sign, or we can multiply by -1 so that it will become greater than 0. So this is what actually the simplex method. So it may have some two major problem with degeneracy and cycling, but it has so many characteristics, so many advantages. Yeah, so if you solve it in a, if you solve it in a minimization problem, then we have to introduce this artificial variables. But there also you can see that this y1, y2. So let us write it v1. This is v1. Let us write v2. Okay. So this is v1. Yeah. Okay. So from here we can see that This will corresponding to u1, this is u2, this is v1, sorry, this is x1, the primal solutions now, x1 and x2. So only thing we have to multiply with -1 to find the primal solutions. Here we have set 2 comma 2. There is a dual optimal. Okay, this is dual optimal. And these are primal optimal. Okay. So if you want to again summarize the properties of uh, primal algorithms, okay, remember these are actually primal algorithms. We are making the given LPP into dual, but still we are applying the solutions. We are actually solving the primal problem, not the dual problem. Although by the characteristic of this simplex algorithm, it actually solves both of the problems, but still this type, the method that we have discussed so far, taking this right hand side greater equals to 0 and following this all the scheme, so we'll call them as a primal algorithm. Okay, so primal algorithm, it has a solution approach is like this. It will the feasible to always the primal solution. So from initial basic feasible solution, it will always evaluate a feasible solution. Okay, so feasible solution. Remember, we cannot start the algorithm without a initial basic feasible solution. So it will always evaluate feasible solutions, and at every iteration, it will satisfy the complementary slackness properties, slackness conditions, and also it will terminate as soon as the dual is feasible. If you go back and check this particular example, yeah, here in the third iteration, we can see that both of them are actually at optimal. Not only optimal, they are just feasible. Just as soon as they become feasible, so the algorithm terminates. But here in the iteration 2, the dual variable y2, sorry, v2 was not feasible. It was becoming negative. So that is why it is infeasible. But here, if you apply, both are feasible. This is v1, this is v2, this is y1 and y2. So if you multiply negative sign, they are actually satisfying their feasibility, and we have reached the optimal point also. As soon as they are feasible, so we have so we can from initial basic feasible solution to the optimal solution. Okay. So can we do the reverse? That means for primal simplex method, feasibility feasibility always maintained. Okay, keeping the feasibility, we have reached the optimal solution. Now there is a method called dual simplex method, which is actually doing the reverse. optimality conditions, all the Cj minus Zj will be less than equals to 0. Okay, this optimality is satisfied, but the feasibility will not be satisfied. So as soon as we reach the we reach the feasible solution, so this direction is actually reverse. The benefit of this method is actually we do not need to introduce the artificial variables. If we don't want to introduce the artificial variables, then we can apply the dual simplex method. So let us discuss with one example. So these two topics are already discussed. So the remaining topic is this one. So we'll discuss this problem with an example. Yeah. So this is the given problem. So minimize this function subject to this constraints. So if you write it in a maximization form, so this will become -4 and -7. If you introduce slack variables x3 and x4, then if you introduce, so we can see that after writing this standard form, we have negative slack is there. So negative slack is also there, but we are not getting the basis. So what we do, we multiply with -1 and make the right hand side negative. But we are getting the basis here. So now this does not have to satisfy these relations for this dual simplex method. Okay, they can be negative. But note that this optimality criteria Cj minus Zj is always satisfied. So optimality is satisfied. The only thing is remaining, we have to find a feasible solution. So whenever we get the feasible solution, so that time we will realize that we have reached the optimal solution. Remember, optimal solution and optimality criteria are actually two different things. This is known as optimality criteria. Optimality criteria. Okay. And the optimal solution, there are two things. Okay. So what we do, there we have calculated, we have found the entering variable, and then we have calculated the theta value. But for this method, what we will do, we will first find the leaving variable, and leaving variable will be the particular one which will have the most negative right hand side value. That means this is, it has much more infeasibility. Okay. So that is why we will find the leaving variable first. Based on that leaving variable, what we will do, we will calculate the theta value. Now the theta value is calculated by this Cj minus Zj minus 4 by that particular row. This is the leaving row is this one x4. So this is -1. So this becomes 4. And then this is -7 by -7. So this becomes 1. And for the basic variables, we do not calculate the theta value. Only the non-basic will enter. And who will enter the basis now? The entering basis will, entering vector will be the particular value who has the minimum theta. Again, the minimum theta rule is actually applied. So here x2 is entering and x4 is leaving. So we have to find out the pivot element. So this pivot element is -7 here. Okay, what will we do? The next step is to divide this row by this pivot element. Okay. So the task is to make it. So this is 0, x3 is 0, and x2 is minus 7. So our task is to divide by minus 7. So 1 by minus 7 is 1 by 7. So 7 by minus 7, minus 7 by 7 is 1. And then 0 by minus 7 is 0. And then 0 by, sorry, no, 1 by minus 7 is minus 1 by 7. And this minus 9 by minus 7, so it becomes 9 by 7. So it becomes positive, so greater or equals to 0, so that becomes feasible. Now we have to find out whether it is feasible or infeasible. Okay. So what we do is, since x2 is a basic variable, so we want 0 here. And x3 is basic variable, so we want 1 here. Only thing we have to calculate this one. So the purpose will be, how we can do that? We will multiply by 3 and add them with the row 1. Okay. So this is very simple. Row 1 plus 3 times row 2 new. Okay, so row 1 we have minus 2. So minus 2 plus 3 into 1 by 7. So this becomes minus 14 plus 3 by 7. So this becomes minus 11 by 7. Minus 11 by 7. And then we have here, what will be the value? So 0 minus 0 plus 3 times, okay, minus 1 by 7. So this is minus 3 by 7. How about this one? So minus 5 plus 3 times 9 by 7. So this will become minus 35 plus 27 by 7. This becomes negative 8 by 7. So it still remains infeasible. Okay, it remains infeasible. So we have to calculate the Cj minus Zj now. So 0 into 0, 0 into minus 11 by 7, 0. So minus 7 into 1 by 7, so minus 1. So minus 1, Cj, Zj is minus 1, Cj is minus 4. So minus 4, minus of minus 1. So this becomes plus. So this is ultimately minus 3. So minus 7 into, so this is basic variable. So let us put 0. Then minus 7 into 1 by 7, minus 1 by 7. So this becomes plus 1 by 7. The Cj is 0. So 0 minus plus 1 by 7 is minus 1 by 7. Okay. Since this is negative, we do not calculate infeasible. We do not calculate the infeasible values. I mean the objective value at the infeasible level. So again, since this is infeasible, so only one negative variable is there. So we have to leave this variable. Okay. And the optimality criteria is also satisfied now. So leave this variable and try to calculate the theta value. So this is the pivot row now. So minus 11 by 7. Sorry, no. Cj minus Hj minus 3 by minus 11 by 7. So this becomes 21 by 11. And this one is minus 1 by 7 divided by minus 3 by 7. So this becomes 1 by 3. Sorry.
Hello, sir. You are on mute.
Sorry. Okay. So the only thing that we have to okay, so if we do that, only thing we need to consider about this greater equals to 0. So these are greater equals to 0. So this will feasibility satisfied. Objective value can be anything as per the definition. So this is negative. So maximize. So the minimum value will become, okay, for me finding the minimum value, what we have to do is, so minimum value will be 1, 2, 3 by 11. Okay, so we have reached. Also, since we are doing the dual simplex also, so since this is also simplex method, so we can see that this is the primal solution. The dual solution here lies here. These are also solutions. Okay. Yeah, that is optimal solution, and the dual solution will here. Now, what we are doing at the moment, it is some observations for this particular problem is, once the right hand side becomes feasible, okay, the variables are feasible, we are reaching the optimality, because this Cj minus Zj is always satisfied for all the iterations. See here, this iteration 3, for iteration 3, iteration 2, it is also satisfied. For iteration 1, it is also satisfied. So the benefit of this dual simplex method is actually it will always satisfy optimality, but the only thing we have to take care of this, the right hand side vector. If they are feasible, we can claim that these are actually optimal, because optimality always maintained. Okay, but if you remember, recall the other simplex method, that is primal simplex method, what we have done there, feasibility always maintained. Feasibility always maintained. The only thing we have changed this row. This, okay. We have to take care of this row, Cj minus Zj. So whenever they have satisfied, optimality satisfied, we can call it a. So feasibility always maintained here, and for dual simplex method, the duality maintained always. Okay. So these two are important and interesting observations from these two topics. So if you remember, this is a dual simplex scheme of dual simplex method. Working scheme of the dual simplex method. Next, yeah, these are some, whatever the story that I have mentioned are actually mentioned, are written here. So please go through it. So this is your practice problem. And I'll take another 5 minutes to quickly tell about one important, two observations actually, two important observations. So first thing is, if, okay, a mixed type of inequality is there. One is greater than type, one is less than type. So for this type of problem, we can see here that the right hand side, we can see here it is greater than 0, but this is less than 0. But we can see that this is Cj minus Zj is actually, this is related to the primal simplex, that Cj minus Zj are actually greater than 0. So this will enter. So whenever, also we can apply the dual simplex here also. since negative is there, so now that we have learned this primal simplex and dual simplex, so we can apply both of them. So whenever the both are possible, it is always preferable. So primal simplex is more preferable. If both primal and if both dual simplex can be applied. Okay, so that is why we are doing the primal simplex first. So we'll enter with this and we'll leave this basis. Okay, so whenever now we can see that this is dual simplex, all the Cj minus Zj are less than equals to 0. So this is dual simplex method. So that is why we first leave this basis and then we calculate the theta values here. So in this particular example, we can apply both the methods and then we find out these values. And the third iteration, we can see that we have reached the optimal solution. So both are actually, so this is primal solutions and these are dual solutions. You can see that x1 and x2, 2 and 1, and the optimal value is 3. Similarly, if you multiply here, is the objective will become again the same value. W is also same. Because the dual coefficients are 6 times. Yeah, the cost of dual is actually here, no? 1 into 6 by 5 plus 3 into 7 by 5. So this is 3 times 7 by 5. y1 y2. So 6 plus 21. So we have to verify this. So let us, whether this is correctly written, we need to verify. Okay. The last thing that I want to mention is the infeasibility. The dual simplex can also become infeasible when we do not find any entering vector or any entering variable, but there is a leaving variable is always. So in that situation, we call it a infeasible solution. Okay. So with this information, I will stop here. If you have any doubt, you can ask me.